In this video, I want to do an example using Stokes Theorem, but I thought we'd start by talking about the curl of a vector field, which means I have to think about del as a vector differential operator. So in the I component, del is the partial with respect to x, the j component is the partial with respect to y, and the k component is the partial with respect to z. If I think about the way we computed del f, where f was some scalar function, that's exactly what we did. We distributed f through and then took the partial of f with respect to x, the partial of f with respect to z, and the partial of f, the partial of f with respect to y, and then finally with respect to z. We treated it like a vector operation. Or at least we could imagine that that's what we did. We just kind of memorized that as a rule, but now I see it as a vector differential operation. To define the curl of the vector field f, I define it to be del cross f. So if I let f be a vector field, and it can be the vector field m in p, well then this cross product is simply this, where I use the vector differential form of del in this middle row, and then m, n, and p, and now I calculate this cross product. All right, so in the I component, I have the partial of p with respect to y minus the partial of n with respect to z. In the j component, I would have a minus, and then I cover up that row and I do my partial. I want it to be a plus though, so I'm just going to change the signs as I go. So I'd have the partial of p with respect to x, but it's actually going to be the minus part, thinking about distributing, and then the partial of n with respect to z is going to be the positive part. And then finally, the k component of the curl vector, cover up the k part, and I get the partial of n with respect to x. And I get the partial of the partial of m with respect to y. And this is actually that differential form that happens in Green's theorem, right? The k component of curl was what Green's theorem was always about. Okay, so there we have it. We have defined the curl vector. So what's the curl vector doing? Well, if you think about a vector field, and maybe this vector field's acting on a surface, this vector is measuring a rotation. It's perpendicular to that point on the surface where this vector field is, and the longer it is, the faster we're spinning around that point. So the curl of f is a measure of spin. Just like the k component of curl was telling me an amount of spin in a plane region, this vector is doing it in a space region, a region over a surface. Now we can look at Stokes Theorem. Let S be a piecewise smooth oriented surface having a piecewise smooth boundary curve C. So I have some surface in space, and I'm calling it S. And around a boundary, I have a piecewise smooth curve S. So here's my surface S, and the boundary curve is called C. So there's my boundary curve around that boundary. All right, F is a vector field, M and P, whose components have continuous first partial derivatives, which means I can actually calculate the curl, on an open region containing S. Then, the double integral over S of curl F dot n d sigma is equal to the circulation around C. And this is the big deal. One way to think about this is the flux of the curl vector, right? Our little n's are little normal vectors. They're normal to the curve. Okay, well this is an important relationship. And if S is a plane region, then this is just Green's theorem, because we end up with just the k component, and n ends up being k, and it's exactly what Green's theorem tells us. Okay, so I want to do an example based on this. And the idea in the example we're going to do is that sometimes the path integral is a little easier to compute. Now, there are situations where you'd use a double integral, and there are good examples you can work through where you evaluate both sides to make sure you get the same thing. But in the example I want to do, we're asked to compute curl F, and that should have a vector hat on it, dot sigma over a surface S, where the vector field is x, z, y, z, x, y, and S is a part of the sphere x squared plus y squared plus z squared equals 4, where x squared plus y squared is less than or equal to 1. So it's just a portion of a sphere. So if we just think about S for a moment, well, I could imagine that sphere of radius 2. And now I'm just going to look for the part of it that lies on the inside of the unit circle in the plane. If I think about x squared plus y squared is less than or equal to 1, that's actually saying the part of it that's lying inside a cylinder, I suppose, here in space. I'm thinking of it as over the unit circle. But let's see, that's 2 units where my sphere's hitting the x, y, and z axes. So let's see. There would be the unit circle in the plane, and if I think about the cylinder that comes up and intersects the sphere, the surface I'm looking at is just this little spherical cap. So S, not the whole sphere. Right, just this little spherical cap. So that's S, and I see the boundary, C, is this. Then that's what we're talking about in Stokes Theorem. So the little spherical cap is my surface S, the boundary around it is C. Well, we're asked to compute this, right? This is the curl vector dot n, so it's written here as curl F instead of in the del cross F notation. And we could certainly work this double integral. We'd have to compute del cross F, we'd have to figure out what n is, and then compute that surface integral through that vector field, the vector field del cross F. But instead, I claim it's going to be easier to just compute the circulation around that path C. And this is what Stokes' theorem says. This calculation should be easier. Now, one cool thing to notice is that I've drawn a surface here that I'm calling S. That's just a spherical cap. So there's S, that spherical cap, and there's my boundary region C. The cool thing to note is that if I just draw C, and then I was to imagine any surface with that as its boundary, so if that's S, then I could think of that, this is S prime. Well, then double integral over that region S prime is going to be the same thing because they have the same path integral. They're going to have the same circulation. And that's one of the coolest things about Stokes' theorem is that actually one approach is you can actually simplify a lot of these regions. But we're just going to compute the path integral, so I need a parameterization for the path C. Well, I know the x and y coordinates come from my unit circle. So cosine t and sine t will work there. And I know that x squared plus y squared along this path is always equal to 1, right? Because that's on the boundary of the unit circle. So if I plug that in there, I'm going to get that z squared is equal to 3, and that z is equal to positive the square root of 3. So another way to say that, that's the height where that circle lives above the xy plane. So to parameterize that path, I could think of it as r of t is equal to cosine ti plus sine tj plus root 3k. Well, to evaluate this path integral, and I should write down some bounds for t here because I'm getting ready to use them. I need to go all the way around it. So I'm going to integrate from 0 to 2 pi of f of r of t dot dr dt dt. So I'll need to take a derivative here. I'm going to need to substitute my vector field, my path into my vector field, and then I'm just computing a path integral. All right, our vector field, xz, yz, xy, And our path was r of t is cosine t sine t root 3. All right, so f of r of t is root 3 cosine t. And let's see, y is the root 3 sine t. And then finally xy, so cosine t times sine t. So now I need to know dr dt. So minus sine t, cosine t, 0. And now we need to take a dot product. And this will become our integrand. So let's see, I have minus root 3 cosine t sine t plus positive root 3 cosine t sine t plus 0 is, well, that is 0. And so my path integral is just the integral from 0 to 2 pi of 0 dt, which is 0. So what we were originally asked to calculate here is just 0, which is the circulation of this vector field around the path C, and it's also the flux of the curl of F.